Hello and welcome back to Calculus 1. We are continuing our related rates section. So this is the revenge of related rates, right?
Yes.
Or part 2.
Yeah.
The return of related rates. So we know that related rates require at least two rates that will be related with some formula. In this case, we started with the ice cube that it's melting in the sun. So as the ice cube is melting, the length of each of the sides is decreasing at the rate dA dt. So the length is lost. And because all of the sides of the cube are getting smaller, the entire cube is getting smaller, which means it's losing the volume. So the equation which relates the loss of volume due to the loss of the length of a side, of the edge of the cube, is given by the formula that we have here. And it's simply obtained by, you look at the basic formula for volume and you take the time derivative, because you want to measure the change of volume in time and change of the length of the side in time, because things change in time. Bueno? Now we've seen other problems as well. This was the airplane problem, the two airplanes approaching the airport. How fast is the distance between the airplanes closing as the airplanes are approaching airport? We have seen the spread of oil as the oil rig starts leaking oil, right? The area for cleanup is growing at all times, and this was just a basic example. We are still to discuss other examples. For instance, one of my favorite cartoon situations. We have a house over here, a happy person in front, and then this guy over here drops a snowball, and we all know what happens, right? Oh, well, you know it's winter because there is smoke, right, from the fireplace. So this is what's happening with these. The little snowball in time becomes larger ball. So we know that a snowball maybe starts having an like that's 2-inch radius, and by the end of the run on the bottom, it picked up a lot of snow. The volume is larger and the radius is larger. So the question is, how fast is gaining the volume, right, when radius is whatever 7 inches. So we can measure the rate of change of radius by observing the photographs that are taken, the action shot, right, of the ball rolling down and picking up all the snow. So if you take the action shot, you can measure the radius on each one of those pictures, and then you take that radius and you can come up with the RDT, right? Since we're talking about a ball, right, which is a snowball, so snowball is a ball, and the ball, also known as a sphere, has radius r. Generally in Calc 3 they call it rho, but whatever. So we have a radius r. We have the formula which connects the volume. Does anyone know? Very good. Well, it's the formula. You were right. So we have the volume for the ball, and then we take the time derivative of it to create the related rates. So derivative of v is 1, and we have dv dt because we took the derivative of v in respect to time, t. Then we have our 4 pi over 3, which is too early. It's way too early for 3r. Going 1 octane up, it's still the same. dr dt. All right, great. And now these 3's will cancel. And then dv dt is 4 pi r squared dr dt, and this would be our mathematical model. So if you provide me with two pieces of information, which is the size of the radius and how fast the radius grows at that time, I can tell you how fast the volume is growing at that time. So what you need to understand is that you actually have three variables here. You have the change of volume in time as a variable, you have a radius as a variable, and you have dr dt, which is change of radius in time as well. So give me any two, I will be able to calculate third one. Now for application, you generally look at what you can measure. If you are taking pictures as this thing situation is developing in time, you can definitely measure the radius off of the picture, and you can also measure the how fast is the side changing, which means that you can compute the volume. So as you can see, the problem is solved because we can say, okay, radius of the ball is 6 inches and it's growing at the rate of 1 inch cube per minute or whatever, and you can get 1 inch cube per second. Doesn't matter. So now we say if the change in radius in time is, let's say, 0.1 inch per second, when radius is 6 inches, find change in volume. Find the rate of change of volume. In time. So if you carefully observe information given, you see that you have dr dt as 0.1 inches per second. First, radius is measured in units of length, which is inches. T is measured in time, which is seconds. So that matches. And then we have r equals to 6 inches. And we have our good old formula. So dv dt is going to be 4 pi, and then r is 6 squared dr dt 0.1. 6 squared is, very good, times 4. Good. And then times 0.1. So 14.4 pi, obviously. 36 double is 72, double that is 144. 144, move the decimal 1 point, and then there's still pi. Are we agreeing on this?
Isn't it 128? Am I calculating on
70, so 36, double that is 72, double that is 144.
Okay.
Because it's 36 times 4, and then, right?
Okay, isn't it? Yeah, okay, it's correct. Okay.
How did you get rid of the inches per second, or you don't transfer that over?
Inches,
Because it's 4.1 inch per second.
yeah.
You don't worry about the inch per second, the second part.
Why wouldn't I worry? I worry about it. Because over here you have inches, and those will be inches squared, and over here you have inches per second. So inches times inches squared is inches cubed over second, which is good because this is volume. Inches cubed per second, right? Now, this was just an example of plugging in numbers. Your actual solution is here. This is what solves the problem. The rest is plugging numbers and shoveling arithmetic around. We have a problem of this snowball rolling down the hill, and if the snowball through time is picking up more snow, which means it's growing in volume. The radius gets bigger, the snowball gets bigger, and in time, right, we can measure the dependent on radius, and change in radius, and change in volume. And they're related through this formula. And then I just added some words and numbers to practice one of those. Next one. Next one is very interesting because it's going to introduce something, and that is, well, this is also one of the possible project questions. You know, it's in a rotation. How fast is the volume changing as you take a sip with a straw from the soda can, regular soda can? You have the regular soda can, right? That's a little bit irregular soda can, but it's a can. Can you please have the can modeled for everyone? Perfect. There we go. So when you have a can, you put a straw, and then if you actually Google this, you will find it. The average sip. Okay, when you do the straw, you can actually Google that piece of information. It doesn't believe me, but there you go. And you can use that information to calculate other stuff. So what do I have? Well, I have this cylindrical soda can here, standing on a desk. Now someone is going to Google the regular dimensions of the soda can, which means I need the radius and the height. Thank you for jumping the gun. So the height of the soda can is, and the radius of the soda can is. Today, while we're still young, please. Thank you. I'm sorry? 5 is the radius, and 6.
Yeah, 5 is the radius.
6. 6.
Are you guessing?
I'm totally guessing.
Wow.
He was guessing. That sounded really confident. Luckily.
4.83 inches high.
4.83 inches high. Okay.
The diameter of the lid is 2.13.
2.13, so that's going to be 1.06 inches in the radius. Great. So here is these are the specs of a soda can. And when you look at the soda can over here, right, we have the height that we can measure. and there is a level of liquid. I'm using blue because I am under illusion that you would drink water out of a can, but you shouldn't, right? I should use green or something that it's not. Doesn't look healthy at all. Or brown for caffeine. Yeah. Red, sure. Like blood. Anyway, so we have stuff in here, and then you have a straw in, and you take a sip. What happens as you take a sip? The level goes down, right? The level would go down. So clearly, I need to calculate the change in volume in respect to change in height. So what do I have? I need the volume of the cylinder. What's the volume of the cylinder?
3r squared times half h.
Perfect. That's great. The area of the base is a circle. So pi r squared is the area of the circle which is in the base times the height gives us the volume of the cylinder. We're going to classify all of that stuff after because you must know these things. Now I am going to take the time derivative, and there is something interesting that is happening in this problem and it did not happen before. Can anyone see what would be different with this formula? And we did not have this happen before.
We have an additional variable on top.
No, this is it. We don't have to think about any more changing the formula. I'm just talking about the formula itself. Before I take derivative, I have to consider what do I have in the formula, so I know how to take the derivative. So can anyone tell me anything about this formula? Yes. Is it the age? What is the age? It's height. What can you tell me about this? Yes?
Does it have to do that the volume is like the height? It's not just like the...
No. Yeah, let me help you out. That doesn't exist. Nothing exists. We're just focusing on the formula. I don't care about the concept. I'm not... Who said product rule? Okay. Who said product rule, right? So, for the first time, we are observing the situation where we have R times age. You know, before we never had the situation like that. Look at this. V on one side, R on the other side. Over here, volume and a side. Over here we have addition between x and a y, right? Over here a on one side, r, right? We never had a situation like this before. And we really want to say, yeah, right? We have r times age, and those are right variables, but is r a variable? See, that's the trick. So now, before we claim that r is not a variable, because it's not in this case, let's take a look at a cone real quick and understand that in the cone, as height is changing, radius is changing. Do we see that in a cone? Do we see that? It's a different radius here, then there, right? It's always the same radius for the cylinder. So, even though this should scream it should scream product rule. It's not a product rule because R is constant. It will be product rule for cone, which is next problem. So, yes, you have to look at the shape, and when you consider the shape, right, you see what you have. So, we have actually this as a volume is equal to pi 1.06 squared h. That's the better version of it because radius is constant everywhere. What's 1.06 squared? I should ask my phone experts in the back because they should have a calculator, but maybe you don't know where that app is. .06 squared. 1.1236 pi h. There we go. Now we are going to take the time derivative and get dv dt is equal to 1.1236 pi dh dt. Now dh dt you can measure because you can observe how much height you lose in time just taking easy photographs, right? Time-lapse photographs, it's easy to measure that. So the amount of SIP that you would research online goes here. So this is a SIP. And you calculate the change in volume. How cool is that? So you can calculate the change in volume. Did anyone Google this? The size of a SIP? Yeah? You can... What happened?
It's in like one straw.
Yeah. Just a SIP. There is an average size of a SIP. For people, yes. $16 milliliters is the average size of a SIP. Now, great, you have to convert that. See? It's a lot of unit conversion and so on. So, 16 milliliters convert. And then plug in, and you will have the change in volume. It's awesome, right? You multiply it by the rest of the numbers, and you will have the... You multiply by the rest of the numbers, and you will have the values. Done deal. Real quick. All right, the next one. And now the next one is my favorite, right? So what do we do here? We're going to have a conveyor belt. Bring in the sand or gravel or something. And it's going to fall and form a conical pile that will grow in time, larger and larger and larger as the more and more sand, gravel, corn, whatever you are dumping on a pile. Whatever, doesn't matter. So now, the incoming stream over here is going to be dV dt. That's your change in volume, dV dt. And you have a cone, which I'm going to draw now on the side. And in this cone, you have the height h, and you have the radius r. Now, what is the volume for the cone? Perfect. Volume for the cone is 1/3 pi r squared h. That's the volume for the cone. So we need to classify all of these formulas so we know how to get them easy. So once we have this, now please note that the radius is a variable as well. We talked about it earlier. Depending on the height of the cone, the radius is different. So now, if you take the time derivative, you are talking about the product rule. So this time around, radius is a variable, height is the variable. Since they both change, they're all variables. So now we have dv dt is equal to pi over 3 is a constant. Kick that outside and just deal with the product rule inside. So product rule, copy the first one, derivative of the second one, plus copy the second one times derivative of the first one. So standard product rule, and you see that the formula is not as nice as it used to be before, right? But it's the formula we have to work with. Now, there is a beautiful thing over here that you guys can do to simplify this, and Mike already mentioned it, and that is similar triangles. You can use similar triangles to eliminate some of the variables. See, when you draw the cone from a side, it looks like a triangle with the height being the height and radius is half of the base. Now, if I just focus on one of those triangles, without worrying on the second one, on the second half, the other half, that's the height, that's the radius. See, I can make this into even bigger or a smaller. See, all of these are what we call similar triangles. So now, if I have that the entire triangle here, let's say this side over here is maybe 5, and this side over here all together, all the way to the bottom. So h is just this piece. And this entire, let's say, is 10. Then we can write the proportion 10 is to h, what 5 is to r. You can put this proportion any way you want. You can say 10 to 5 is h to r, whatever. So now you have 10 over 5 is equal to h over r, from where h over r is 2 and h is equal to 2r. Now it's obvious the h equals to r because I picked 5 and 10. Pick any numbers, that ratio 2 is going to change. So now I have a relationship between the height and the radius, and what I can do is hit that with a time derivative and obtain dh dt is equal to 2 dr dt, and that is going to simplify our formula up there, because you get to plug in, let's say, and eliminate h, or you can eliminate r, depending on what you need. Because you have two equations here. You have two equations that will eliminate either h from both or r. So they're connected that way. So now let's say you want to eliminate h because it's already there. So now your dv dt is equal to, we have pi over 3. Now remember, we are eliminating h. So we have r squared, and instead of dh dt, I have 2 dr dt. Plus, I have 2r and then h. So 2r, and instead of h I have another 2r. And then I have dr dt. When you carefully work this out, what do you get? You get 2r squared dr dt plus 4r squared dr dt for a total of 6 r's. 6, there we go. 6r squared. And then pi over 3. So we have pi over 3, 6r squared dr dt, which is equal to 2 pi r squared dr dt. This is one of the ways that the problem could take turn depending on what you need. So now, as you can see, your related rate here, well, I'll write one more, dv dt is equal to 2 pi r squared dr dt, and you can measure those and you have it. So you plug numbers in and you know how fast the value is changing. What value? It's the volume. It's the volume. It's the amount of stuff on a pile. Right? That's all we care about. How much stuff? How much stuff do I have on this pile here? Which is volume. But I also want to know how fast is that changing, because maybe we need to design a system that will shut off the conveyor belt and prevent it from bringing in additional corn or whatever we are dumping on the pile, right? Because if this gets all the way to the top, it will start accumulating stuff here and eventually going to break the conveyor belt. So we don't want that. These things are very expensive to install, maintain, and all of that. All right, it's time for us to categorize the volume, talk about volume. And this is where you're going to learn all of the formulas for volume out there. It's categorized in three different categories. First category is going to be prisms. So we have cube and a box, rectangle, right, and the cylinder. So they're all in here. Maybe you have a triangular one, that's fine as well. So whatever is like that. And the volume is simply base times the height. So B is area of the base. And capital H is the height. So note, we have a square, we have a rectangle, we have a circle, we have a triangle. You should be able to calculate those areas. And you multiply by the height of the object. So there's always a height associated with the object. And area of the base is actually... So when you are dealing with a cylinder, cylinder has a circle in its base. right? If there's a circle, the area of that circle is pi r squared, and then times the height. Pi r squared times the height. It's exactly the formula we need. So prisms are going to work that way. Whatever the shape of the base is, you will just simply multiply that by height, and you're done. The next section of the next type is what I call spiky objects, right? Spiky objects go into a spike on the top. So our candidates are cone, pyramids of various shapes in the base, and so on. So if there is a spike on top, volume is going to be 1/3 base times height. All of them. So I don't care if your base is a circle or a triangle or 9 sides, whatever it is, it's always going to be 1/3 of base times height. And finally, we have the perfect object, the only one in its category, and that's a sphere, ball. Volume is 4/3 pi r cubed. That's the end of the story. So this is how you categorize all of the volumes out there. And all you need to ask yourself is the question, is the object spiky or not? And obviously, is it a ball, right? But you know that the ball, that will be a sphere, right? And something like that. And now the last part would be for us to consider some kind of engineering design, because we can. Now for that, I usually like to play a video for a few seconds. Oops. Yes. This?
No.
Oh, this?
Yes, this.
So the video that I want to play now is the launch of, well, Falcon Heavy, but we can do also Falcon 9. I think Falcon 9 was the better. Let me see. Yeah, we'll do this one. All right, perfect. I'm not sure where the sound is, but doesn't matter. Oh yeah, there. So this is exactly the part that I need you guys to see.
6, 5, 4, 3, 2, 1, 0. Ignition, liftoff.
This part. So this shot, right? Is this Joe standing next to it? Holding the camera? No, right? A lot of this stuff obviously is done with drones. But how about we design a system that will capture this from the camera that is on the ground, and we'll let the computer actually take the images. By the way, what are those numbers on the upper right? First one is the speed, and the second one is the altitude of the rocket. Great. So I have those two always given, right? I can feed that information into the computer, into the software, because I need those numbers at all times. Sounds good? All right, so this part over here, not so good, right, in terms of the shot. The rocket is not really in the center of the shot, right? It's in the bottom of the screen, but that's okay. So this was a Falcon 9 launch. This video is 20 minutes or so, no, 9 minutes long.
It's the Merlin vacuum engine, which you heard is just beginning its own.
This thing is now approaching 5,000 miles per hour. I mean 5,000 kilometers per hour. It's gonna go soon, 5,000 miles per hour. Don't worry about it. It's gonna go 11 and then 12 and then 13,000 miles per hour. So you know when you're pulled over next time for exceeding the speed limit of 65, understand that we are able to achieve 11,000 and more. Anyway, it's going to be a separation here. There we go. Perfect. Really cool. Okay, good. So you've seen the video, and now let's design a system for this. We're going to put a servo motor on a controller, right? Controller is going to have the mathematical function, so that's what we need to develop. All of the electronics and things that already exist, you need to put them together. That's easy, right? Okay, Mike has everything in his car, so maybe we should just bring everything in and let's just do the stuff right here. I just need the volunteer to be launched in the orbit, preferably someone who believes the Earth is flat. Oh, quickly. You quickly let your hand down on that one. Yeah, I can see the NASA shirt, but had to pepper in the.
There's about 100 official members of the Flat Earth Society.
All right, there we go.
Can I put them all in one? All right. Here's what I'm going to do. The camera is going to sit in this thing over here. That's the camera. Look at that. This camera is so 1950s, right? Now, we're going to have our rocket. Maybe I should ask some of my... how about this? There we go. Look at that. Look at that design. Could I have a spike over here? There we go. Perfect. This is Space Nick. There you go. Launch this. It's gonna go at least 10 feet in the air. We launch high. What's happening here? Our camera is going to shoot so that the rocket is always in the middle of the shot. What do I need to design? I need to design a system that will turn the camera around this pivot point here. There should be a tripod over here. The camera's going to fall off. And that's going to be changing the angle in time. We call this omega angular velocity in physics. So observe what's happening. This is the level shot here, and then eventually there will be some angle theta. You know that we are trying to turn this, so that's our d theta dt in time. Usually when I teach this, I put this to be 500 feet, and we have the height which is given to us from the central command. Sounds good? We also have, well, now what is the geometry of this problem? (2D or 3D? 2D, good. What is the geometry of this problem? Right triangle, thank you. Here it is, right triangle. Do we all see a right triangle over here? We do? Good. So we have a right triangle, and we have these pieces of information. So I have these pieces of information. So what do I use to connect these pieces of information? Trigonometry, very good. Now, which trigonometric function should I use out of 6 of them if I have opposite, adjacent, and the angle? Tangent, very good. So, tangent theta is opposite, which is hypotenuse divided by 500, which is the adjacent. From where I have that the height is equal to 500 tangent theta. I will take time derivative here to get the related rates. So that's dh dt is equal to 500 secant squared theta d theta dt. Now, dh dt is equal to 500, and now, oh sorry, I need to move everything to the, I need d theta dt alone, right? Because that's what I'm looking for. I'll explain why. So now I have dh dt 1 over 500 secant squared theta, but 1 over secant squared is what? Cosine, very good. So cosine squared theta over 500. Here is my formula. This is what I'm supposed to program in. This one is what? This is your omega, your angular velocity. This is the speed at which you turn the camera. This is the height of the rocket. Sorry, the speed of the rocket. Oops. Speed of the rocket. We know that as well, right? And then current angle. You will be updating this as it goes up. So all you need to do is to program this part of the formula to compute this thing over here, because d theta dt is what turns the camera, and as you can see, when the speed at which you turn the camera is linked to the speed at which the rocket goes up, the camera will always have the perfect shot and the perfect, right? The rocket will be always in the middle of the shot. You're updating the angle, you're updating the height, the speed of the rocket, and you will be able to program in servo to turn the rocket, right? So please have this ready for next class. Well, if he goes home, he cooks this in the afternoon and comes back, so. There you go. So this is a basic engineering design, guys, and this is what you get the money for. I mean, you get paid money for stuff like that. So you have to figure out how to put all of these, X's and Y's and so on. So as I said, the previous stuff in a chapter, taking derivatives and all other, the rules and things like that. Yeah, you know what I want to say, right? But when it comes to 3.11, that's where you make your money. Whether you are working on the ice melting committee, or you are designing some of this stuff, or you put the, designing the system to shut off as you piling up gravel or whatever on a pile for conveyor belts or whatever. You are some kind of engineer, and this is your section. Yes? No, because inverse trig gets you the angle. Yeah, you need the speed, and that's the related rates. Figure out the geometry. Is it 2D or 3D? If it's a 2D, what are we talking about? Are we talking about area? Are we talking about perimeter? Pythagorean theorem, one of the trig formulas, circumference of the circle or something for 2D. If it's a 3D, well, we're probably talking about some kind of volume. Volume related to the side of the radius, or side, the edge of the cube or whatever. And then when you have the formula from the geometry of the problem, you will take the time derivative. When you have the time derivative figured out, time derivative will tell you what is the next, what is the formula that you use to connect the rates and calculate what you want. And that is the related rate section, and that is the end of chapter 3. There we go. All right, bye.